This is Math 315, History of Mathematics. We're picking up with Chapter 12, a transitional period. In the 17th century, this is the time we're trying to set up our calculus now. Some key people here, we have John Wallis, Nicholas Mercator, Christian Huygens, Abraham de Morve. With some key concepts, like I said, we're setting up calculus. We have some estimates of area, infinite series. We're looking at some probability topics with expected value and Bernoulli trials, and then annuities. Alright, so again, this is the bridge between analytical geometry of Descartes and the calculus of Isaac Newton. John Wallis wrote Arithmetica Infinitorum about these topics. And so we're going to look at a question considered by both Fermat and Wallis. And the question is, find the area bounded by the parabola y equals x to the k. The x-axis on some vertical line we'll pick to be x equals 1. So this is very much a Calculus 2 discussion, and we'll show that John Wallis was looking at these things by this method. So here we want to take our curve. This is our curve here, and we want to divide it. We're going from 0 to 1. We're going to divide it into n subintervals. And I'm just going to zoom in for the sake of our discussion here. Alright, now the left, so if you've been in Cal 2, you know what we mean by the left endpoints is that we're picking the left endpoint of each rectangle, whereas on the R, we're using the right endpoints of each rectangle to touch the graph, and those determine our height. And so we're going to estimate the area under the curve by adding up the area of these rectangles. And these rectangles have area, but 1 over n times some height, and that height's dictated by our function. So for example, this one here would have endpoint 3 over n to the k power. And so the height of that green rectangle is 3 over n to the k times 1 over n. Okay, now if you think about the way this is set up, my rectangles here start out from the 0 spot up to this height here would be the n minus 1th position, where on the right we start at the first guy. I'll just mark it. This is the first endpoint up to the nth. So if you plug this into our function, we can deduce then that the area of the curve has got to be between this L and the R. And so L would be 0 to the k plus 1 to the k up to n minus 1 to the k over n times n to the k plus 1, right? Because this would be 0 over n to the k times 1 over n plus 1 over n to the k times 1 over n, and etc. up to n minus 1 over n to the k times 1 over n. And so that turns into this. On the right hand side, we do the same thing, except we start with 1 and end with n. And we know the area's got to be between these two. So in our calculus class, we have a simple solution for this. We can just integrate. And we know that this integral 0 to 1 x to the k dx is just 1 over k plus 1. Did John Wallis know this? He had a feeling, and so did Fermat. We know that as n approaches infinity, these L and R's have to go to 1 over k plus 1. Fermat knew this. He wasn't able to prove it, but he held it via investigation using an Egyptian formula by Ibn al-Haytham. And this is not ancient Egypt, but it's still pretty old, and it's impressive that he had this formula. It's impressive Fermat knew it as well. Then the Englishman John Wallis deduced it as well, but he did not prove that the limit was 1 over k plus 1. But we can show what something Wallis could do, and this is a special case. If for the graph y equals x cubed, we could actually do use some of our formulas to figure this out. So our sum here, so notice that if you have n sums of n cubed, that's n times n cubed. So that's how we would recognize it in our previous example. And actually this should be r, since we're starting with 1, ending up at n. So this is our right hand limit. Okay, so here we have 1 cubed plus 2 cubed up to n cubed over this n times n cubed. We have shown, though, a couple times now a formula for this, and we know that that's going to be n squared times n plus 1 quantity squared over 4. And so if you think about it, that means that we have the limit as n goes to infinity of 1/4 times n squared plus n plus 1 squared over n to the 4th. So if you multiply this numerator out, you're going to end up with a power of n to the 4th over n to the 4th, and so this will be simply become 1/4 times 1, or just 1/4. All right. Now, we'll show some more examples of the mathematics from this time period in the next video. Please let me know if you have any questions.